Hi gang, this is going to be your centripetal force lecture. So this is going to be relatively simple for you guys, but it is something we need to cover, and there are particular points that I need to make and make sure, and some mistakes that we need to eliminate before we go any further with this. So, what is our centripetal force? Okay, well, so real quick review. We've got our circle, and remember that we've got, let's say we have a velocity, or traveling this way along the circle, and as we travel along the circle, our velocity is going to change our direction. So we'll have initial velocity and we'll have a final velocity. And with our initial velocity, we'll also have an initial r and an initial final, and a final r. So as we go through, okay, we find out that we have a change in our position as we change our velocity, and that's our delta r right there. Okay, and that's if we travel through an angle theta. And so if we compare our velocities, then our the change in our velocity is going to be through an angle theta. Okay, and that's going to give us our delta v, and our delta v is going to be related to our theta that we've turned with our velocities. Okay, and so we can get this proportional. What we have here are these similar triangles where delta r over r is going to be proportional to delta v over v, because they're both opposite theta and they're both isosceles triangles. And we have the, if we multiply them, just because we can, by 1 over delta t, okay, which is really just determining the rate of change of these. Okay, we find out that 1 over r times delta r over delta t equals 1 over v times delta v over delta t. And if we take the limit of this as delta t approaches 0, we discover that 1 over r times our velocity, of any kind of velocity, is going to equal, in fact, let's get in here a little bit and make sure that we have our vectors in here. For both of them, because there's r down there and r down there. Okay, or we wind up that our acceleration vector is v squared over r in the negative r hat direction. We did go over this in class that one day. If we think of it like, if we're starting, because we're measuring from the origin, so our r vector, our position vector, is how far away and in what direction from the origin. Well, if we take the origin to be the center of the circle, then traveling in the direction back towards the center of the circle would be the negative r hat direction. That's how we get that negative r hat. Okay. But what if the curve changes? What if we don't have a uniform circular motion and we have some other kind of curve? Well, in that case, let's say we have a squiggly curve there. Well, we can find places along the curve that are parts of different circles. So, so there's a circle right along there, and that curve would be tangent right at that point. And so the radius of curvature, okay, so that circle represents that portion. Then we have another tighter circle over there. And then in between those two, we have even a larger circle. And so we have 3 different circles. And if we have 3 different circles, then we're also going to have 3 different radii. And these are the radii of curvature, or we have multiple, if you have, radii is the plural for radius, and so those would be the radii of curvature for our 3 circles, R1, R2, and R3. Okay, and also all those are the radii of curvature. Okay, and those are the R for the acceleration, for the centripetal acceleration along a changing curve. So we have to find out what the curve is like along that particular point, what a radius of curvature is. Okay, so imagine this. We have a car, and if you're a new driver, I remember when I was brand new, I did this all the time because, at 16, 17, we'll say 18 years old, teenagers don't think a whole lot about the immediate future, or don't tend to not plan ahead. So when they're driving and they see they have a right turn coming, perhaps they don't slow down as much as they should, or perhaps they get a little too far out into the intersection, and then they turn right away, and so they get this kind of a turn where they go straight out and they hard turn to the right, and they find out that their tires squeal, and they throw their well, if you do it right and you've got a bench seat and you've got your significant other in the seat next to you, you can kind of get him or her to slide over next to you. If you turn real tight, but that's probably not the slyest way of making that happen. But you notice that the radius of curvature is really small, and that the circle that it's creating is a very small circle. And as the radius decreases, right down here, okay, so as this radius decreases down here, your acceleration is going to be significantly higher if this goes down. So those of us that we get older, and because we tend to be safer and wiser, and well, frankly, just older because we can't handle all the forces that it would take otherwise, we decide to round out the turn a little bit, and we start a little early, okay, and we cut into the corner a little bit more, and this makes our radius of curvature quite a bit bigger, and so therefore our centripetal acceleration, again, if we have a really large R, then our centripetal acceleration is going to be a lot smaller, and it's something we can handle with our curve. Okay, now let's get back to Newton's second law here. So our net force is again equal mass times acceleration. Okay, and so if we're traveling in uniform circular motion, how do we use this with uniform circular motion? Well, our net force, if we're traveling in a circle, is in that direction. It's going to equal mv squared over r hat. Okay, so how do we use this? Let's say we're on the International Space Station. Okay, we're on the ISS, and so the only force acting on our object that's traveling in a circle is and we start spinning something. We spin something around on a string, and we make it travel in a circle. And so the only force acting on it is is our tension that's holding our thing from in a circle. Okay, so how do we describe our free body diagram? We begin the procedure. Well, in this case, it's just going to be the tension pointing towards the center of the circle. Okay, but when we do this, we need to label the forces as what they are, not as a centripetal force. A centripetal force centripetal in this case is an adjective that describes the direction of a force, not what causes the force. So gravity can be a centripetal force. Tension can be a centripetal force. Friction can be a centripetal force. Remember, centripetal just means center pointing, or center, or towards the center. And so there are any number of forces that can be the centripetal force keeping something traveling in a circle. So when you're drawing your force body diagram, so we pick our axes, and x is towards the center. Again, our sum of our forces equals m times max, and then so our tension in this case is mv squared over r. They equal each other. However, do not put Fc, centripetal force, as when you are labeling your forces. Okay, we know it is a centripetal force. We know it has an acceleration that equals v squared over r in the negative r hat direction. Okay, but there's something else causing it. There's something that causes that force to happen. That is what you want to label towards the center of your circle when you're traveling in a circle. Okay, so do not ever do this. That is a no-no. Okay, so let's do something else. Let's imagine a car doing donuts. We described that a while back. We had the open parking lot, and with no LDs and no police and no curbs around. Okay, and so we're going to look at it from the end again. And here's our car, and it's traveling in a circle. So we have gravity acting on it, and if there's gravity, there's going to be normal force. But then there's also going to be a force pushing it towards the center, and it is friction. That is what's keeping the car traveling in a circle, is the friction force between the road, okay, and the tires. So the sum of our forces in the x direction we only have one force in the x direction. That's our centripetal force. In this case, it is friction. Okay, and in the y direction, well, we have normal and gravity, and since we're not plummeting towards the center of the earth, or we're not being lifted up into the sky by the ground, those two are going to equal each other. And so our normal force plus mg equals 0, or normal equals negative mg. And so what's really happening is that we have our tires that are spinning on the ground, and there's an interaction right here that between the force, between the tires and the ground. Okay? And that gives us our friction, because it is a static friction, because as we said in our friction lecture, that we don't want our tires losing their static friction with the ground. Okay, that's when we start sliding, we get to, we start hearing the squeal of tires, because they're, somehow, somewhere, a car has lost control. Okay, so let's find out what usually happens here is we get the question that asks for the maximum possible speed to keep the car still traveling in a circle. So if we go over that speed, then we become kinetic friction, and we start sliding around. So let's find what that speed is. Well, we know that our friction, because friction equals our centripetal force, and here's our friction. We're going to set it equal to each other because we want the maximum possible speed. So we're going to set our friction force equal to our mv squared over r. Okay, and that gives us, this winds up giving us a velocity now. I can do the math slowly, but you guys can figure it out. If we solve for our speed, then we get mu gr over m. I think that's right. Oh, no, that's not right. Hold on, I screwed up. Because normal force equals mg, and so our m's are going to cancel each other. So I thought it was going to be all sly and do all that, so let's do the math here. Alright, so this is going to become mu s times a negative mg is going to equal mv squared over r. Well, our m's are going to cancel. And so really we get, okay, so we just don't have the m anymore. So our v squared is going to equal mu static gr. Then we square root both sides, and we get v equals square root of mu s gr. And this would then be our velocity, for our maximum velocity for keeping our car in a circle. And that's how we deal with centripetal force. So take good notes on that, and good luck on that homework.